All right, so this project is to develop and benchmark data simulation methods on a standardized test bed. Now we add a new friend, that's the red curve on the right. So if we're able to do data simulation that takes in the most recent stream flow to predict tomorrow, we get a lot of performance boost. So this is very interesting. What's going to happen? Okay, so we will test a number of data simulation methods, including ensemble common filtering, the traditional method, but also with the machine learning models and differentiable models, you also get the gradients. So you also can do things like variational data simulation and a data integration that you directly feeds in, where it directly feeds in the recent observations. So we'll test a number of different models and a number of different simulation methods that will allow us to kind of fairly assess these different methods and models. That's the core idea. Thank you.
Hi, everyone. I'm Adrienne Marshall. I'm not Glenn, but I'm working on a project with Glenn Tootle and Lisa Davis, who are both at University of Alabama. I am at Colorado School of Mines. We're working on a USGS-funded CIROH project where USGS mentioned they've been developing their enterprise capacity model. And so we are interested in essentially evaluating model uncertainty and looking at how perimeter uncertainty within this enterprise capacity model affects forecasting uncertainty. We're particularly interested in taking a look at some uncertainty in the snow and soil moisture observations that might get used to calibrate the model. And we've proposed to do some tests in two small data-rich basins in the headwaters of the Upper Colorado River Basin. I'll leave it at that and happy to chat any more with anyone who finds me later. Thanks.
Thank you.
Hello, everyone. My name is Mohammed Abdelkader. I'm working with Dr. Tamimi, the PI for this project. After receiving the award yesterday, he left. I hope that he did not leave to skip paying for lunch or celebration. So our project is entitled Leveraging the USGS National Imagery Management System for an Operational Monitoring of Stream Flow Condition using Computer Vision. I believe the title of the project summarizes the scope of the research, but I want to emphasize on one thing, which is the database that the USGS possesses now. It's composed of 569 stations. 8 of those are located in Alaska, and one station is located in the middle of nowhere in southeastern part of the Black Sea. But I think that's something that we need to report to the USGS because the station is located in New Jersey, but there is mistake in the mapping. Regarding the method, we'll leverage those cameras to retrieve reach-based information. So there are different methods well established to get water level, velocity, and stream flow discharge. And those measurement or information will be later on posted online, and that's ultimately the goal of the project. For any suggestions, comments, please reach out to Dr. Tamim.
I'm not Mackenzie, but she's the PI on the project, working with Chris from University of Vermont, Jeff Horsborough from Utah State University, and we have a project to advance snow observation systems to improve operational stream flow capabilities. So what are we doing? The problem is, talk about snow, in-situ observations are far and few between. The location of those is not really designed to have a comprehensive understanding of watershed sweep, but to have statistical reference to from a snow location to stream flow in a mouth of a river. And so we're going to be developing and deploying low-cost Arduino-based instrumentation throughout a watershed so we can improve our understanding of catchment, snow water equivalent, and then put other sensors on there. So we're going to develop low-cost sensing systems. So we'll have snow or wind speed, radiation sensors on there, snow depth, and then we also got to improve the communication system. How do we get a low-cost way to transmit this kind of information either to a centralized location or somewhere where we can use it? So we'll be using data standards, and I will leave that with Jeff. If you have any question on data standards, yeah, he's a great resource for that. And then we're going to be working with local municipalities, particularly for my part, is Salt Lake Department of Public Utilities, using the Logan River Observatory, and then Mackenzie be working with the USGS and some of their sites in Colorado. Thank you. And there's cool drones and making fun things with science.
Hello, Falava, everybody. I'm Chris Schuler, and I apologize. I didn't get the message about putting my name up there, but I work at University of Hawaii Water Resources Research Center, and my collaborators working on this project are all also at University of Hawaii. And so our project is, I believe, the first and flagship project in American Samoa, or any of the U.S. territories. And American Samoa doesn't really have the weather forecasting creature comforts that we enjoy in CONUS. So we're on this project working to fill some of those gaps, really by boosting the monitoring capacity. There's no weather radar in American Samoa, and there's only one meteorological station. So we're telemetering some of our meteorological stations, telemetering stream gauges there. And then we're also going to be trying to use some novel forecasting techniques to get better precipitation data in lieu of those lack of radar data sets. Thanks.
Hello, everyone. My name is Hongxin Liu from University of Alabama. This project, we are going to advance USGS water quality monitoring and prediction capability using satellite and drone remote sensing technology. Our team members from 3 universities, University of Alabama, University of Vermont, and Louisiana State University. For this project, we have focused on 3 group of key water quality parameters for freshwater rivers and lakes. The first group is a coffee concentration, algal bloom, and the biomass. A second group, that's stability, clarity, and sediments concentration. And the third group, that's sit-down. So the first specific objective for this the product is construct comprehensive testbed data sets, which consists of remote sensing data and the simultaneous field measurements. The remote sensing data we are going to use the primarily include Sentinel-2, Landsat 8 and 9, and also high resolution planet supernova data. We are also going to use drone to acquire super resolution hyperspectral remote sensing data for this product. So for the field measurements, we are going to use 2 different approaches. The first approach, we are going to use multi-sensor mounted on a autonomous vehicle to get water quality in situ measurements. Second approach, we are going to acquire water samples for lab analysis. The second objective, we are going to develop atmospheric correction methods and land adjacency factor correction methods, which is very important and critical for water remote sensing. A third, the most important part, the objective is to using deep learning and GeoAI technique to develop robust remote sensing inversion models, eventually translate remote sensing image, multispectral imagery and hyperspectral imagery data into water parameter maps. That's a kind of a brief introduction for what we are going to do.
Good morning, I'm Marian Masti, and my colleague Ibrahim is here, and we have another colleague from USGS Illinois as Kopiai. So the need for this new stream flow monitoring method was generated from the lack of systematic studies on hysteretic behavior associated with flood wave propagation, the steady flow, non-uniform associated with the flood wave propagation, and which appears in our literature as loops. That's quite reported and known. And something which is not reported is the phasing between the variables, the stream flow variables, with slope picking first velocity, Q, and last is the depth. A similar hysteretic behavior occurs at the yearly scale due to the change in the vegetation status. There is another cycle going there, and they are not analyzed systematically. So this is why we do this study, and that's why we developed a method which basically combines some components of index velocity method, if you are familiar, slope area method, continuously apply at a very high frequency, we can go down to 1 minute. And we have now for this project a super instrumented site where we measure variable gradients at the reach scale to capture basically all the variables in San Venant equation. And then with this information, we will do several things, understanding better the phenomenon, both trying to assess what we need to have these things captured, and providing data sets for assimilation in near real time, which velocity, index velocity is not used to be in the forecasting model to this forecasting flow. And providing some information, practical cost-benefit information on various configuration of measuring the flow. Thank you.
Morning all, I am Sierra Young and I'm collaborating on this project with Jeff Horsborough from Utah State and Irfan Goharian from University of South Carolina. And our project is broadly focused on the operational requirements and challenges of using cameras as for non-contact streamflow monitoring. Through this project, we're going to be looking at a few different things. First, we're going to see how readily can we implement existing algorithms and approaches to process imagery and video, what kind of calibration or model retraining are needed for new installations. We are also going to integrate cameras into existing operations in the Logan River Observatory, and also an experimental watershed in South Carolina, and how valuable and meaningful are the data that we can extract from cameras, looking at things such as surface velocity and depth. And finally, throughout the entire project, we're going to be assessing the operational scenarios for and the trade-offs of using different cloud and edge computing architectures and strategies for scaling the use of mini cameras within these ongoing operations. So the goal of this project is to ultimately develop a set of key recommendations for practitioners and others looking to integrate cameras into ongoing monitoring operations.
All right, this is the last time you guys have to see me up here. Once again, kind of furthering our modeling work, but rather than just focusing on the Western U.S., we're also going to expand it to other regions. I am still focusing on the Western U.S., basically Rockies to the westward to the coast, Pacific Ocean. We have Andy Wood, Colorado School of Mines, who'll be really helping out with our evaluation and testbed framework. Kate Hale from University of Vermont, we're going to explore basically underrepresented snow research reasons, research locations, particularly in the Northeast United States. And then Mackenzie's going to continue to contribute, help with that Northeastern component of transferring some of the snow modeling work to that area. And so just we're going to enhance our national snow model. We're going to basically be model domaining or optimizing the modeling domain. We like to go from 23 separate small regions to a greater one machine learning model to grow our 20,000 square kilometers to the entire Western US, not in a rectilinear grid per ed. And we're also going to be looking at other real-time products to put into our model. Right now we're putting FERS model data in there. And we're going to reduce that 3-day time lag to a single day and other remote sensing products. That's it. And there's implementing the NDSI, we just kind of see a great improvement in matching what some of the snow-tail observations are within the appropriate elevation band. Thanks.
These titles are reversed. I'm going to go first. You've heard about Atlas 14 and 15 mentioned several times over the last couple of days. I realized not everybody knows exactly what they are. Debbie and I are going to cover those on our 2 projects here, so we get 2 minutes. I just want to make sure you know. All right. Say you're in the land development business in Alabama and you want to put a culvert under a highway. Well, the state regulations say you must go to the Alabama Department of Transportation hydraulic manual, and it will tell you that you must size your culvert to handle a 50-year return frequency or a flood with a 2% chance of occurrence. How do you know the 2% flood? Well, the manual says you will use the 2% precipitation for that location, and you find that in Atlas 14, Volume 9. With recent legislation, these volumes need to be updated every 10 years. So in the short term, we're updating 2 volumes covering these 9 states and Washington, D.C. We're looking at multiple statistical methods in which to do this. And importantly, now that we need to do this every 10 years, how to do this very complicated process much more efficiently.
Oh, you had a figure. That's pulled directly from the precipitation frequency data server and how the data are delivered on the line. I'm going to talk about Atlas 15. So Atlas 14 assumed a stationary data set. And so now we are tasked with looking at a non-stationary approach. And so for Atlas 15, we're evaluating or reevaluating the approach that was laid out in the assessment report in 2022. So we're looking at methods to improve and enhance the identification of the spatial and temporal covariates that we're going to use to model the data. We're also going to incorporate historical trends from the observed data. We're looking to improve regionalization techniques so that they're more robust and can be done in a more automated fashion, because we are doing this as a seamless CONUS-wide grid as well as OCONUS areas, and then particularly spatially mapping in between gauged locations of observed precipitation data. We're also working on future climate conditions. So we're teaming with Dr. Ken Kunkel at NC State University, who's got a lot of experience with the global climate model data. And so we're going to evaluate the appropriate downscaled CMIP6 data. There aren't a whole lot to choose from right now. That data is relatively new. And so we're looking at working with another CIROH member from University of Wisconsin on some downscaled data that we can use. And the particular challenges for the future climate conditions is really resolving sub-daily durations, because global climate model don't do a good job at sub-daily, and we need to go from 5 minutes through 60 days. So we're evaluating ways to look at that, as well as creating more robust estimates beyond 1 in 100. But the method that we're using, maximum likelihood estimation method, does a fairly good job out to 1 in 100, but we need to get out to 1 in 1,000. So we're looking at ways to do a more robust analysis for that. Thank you.
Hey, good morning, everybody. So our project for FY23 is a 1-year proof of concept to incorporate volunteer emergency management organizations in collecting high watermark data in some of the more severe environments. Right now, there's a team from the USGS that's tasked with collecting this type of information in the field, but without being a first response organization, they do tend to have to wait until a lot of cleanup and response and rehabilitation has taken place. And oftentimes there is some lost data in that sense. So we're working specifically with the Civil Air Patrol, which has 30,000 cadet volunteers and 36,000 senior member volunteers who are actively involved in search and rescue and disaster relief operations in 3 phases, more or less, doing a train the trainer with several key personnel across the country, and then training cadets and delivering field maps and ArcGIS online tools to collect this data in real time. Thank you.
Thanks. This is kind of a follow-on project that connects into the original testbed project. And one of the best way to think about it is it's kind of a handshake between RFCs and NWM Next Gen on ensemble forecasting. And so it's just, there are a number of people included. We have 3 RFCs that are participating formally: NWRFC, CBRFC, MARFC, as well as a team that includes some other CIROH members. The basic idea is to drill down into a test bed that's already been established by OWP for HEFS ensemble forecasting. It's about 97 basins around the country. We'll do some hindcasting and evaluation with the HEFS, and then we'll try to mimic some of that within a next-gen formulation. So we have ensemble forecasting in next-gen, and then at the end of the project, we'll go back and try to cross-fertilize between the two, where we see advances in HEFS or in the next-gen ensembles that seem to benefit on the other side. We'll try to bring them across. So that's in a nutshell what the project's about. Thanks.